Welcome to another video in this series of explaining my research. So today I'm going to be looking back at this paper, the effects of surface stripping zinc oxide nanorods with argon bombardment, which was published in IOP's Nanotechnology in 2015. And this paper is particularly important to me because it's gone on to inform some of my later research, including another two papers which are very similar techniques to this, and also further papers which explore the same sort of science but with a different aspects, and of course I'll be making videos on that for this series later on. So in this paper what we did was argon bombard zinc oxide nanorods or nanowires, and then looked at the electrical conductivity, the defect chemistry, and also looked at the physical changes with scanning electron microscopy or SEM. So we grew some nanowires using a hydrothermal method. We then rubbed those onto a piece of silicon so they were lying sideways on. We looked at them in the SEM and you get an image which looks similar to this. We looked at it under photoluminescence. So photoluminescence is a technique where you shine a laser onto your sample and you look at the spectrum of light coming off. So with zinc oxide what you expect to see is a peak at around 380 nanometers, which is the equivalent to the band gap in zinc oxide. So this is what light that it naturally emits or absorbs at. This is why it's used in sun cream, because 380 nanometers is UV. And also, as you see, as you get this big peak, and if you look closely, this larger peak is made up of a series of smaller peaks, and these are related to defects. So zinc oxide is a crystal where a zinc atom is bonded onto an oxygen atom, and on the other side of that there is another zinc atom and another oxygen atom and so forth, and it forms a what's known as a Versorite structure. I'll make another video which really explains zinc oxide and its properties. However, the defects we're talking about in this case are vacancies. So there are many different types of defects, and vacancies are where there's missing atoms, and we're particularly interested in oxygen vacancies. So this is where oxygen is missing from that crystal lattice, which means that they are electrons which would be bonded from the zinc into the oxygen atoms, and because the oxygen isn't there, those electrons from the zinc are there just hanging in space. Or sometimes the oxygen vacancy will form after the oxygen has initially bonded and will take those electrons away with it. So we'll come on to that later in the video of why that's so important. So the original idea of this research was that we use argon bombardment to clean the surface of the zinc oxide nanowires. So argon bombardment is a common technique for cleaning semiconductors, and zinc oxide is also a semiconductor. It's a wide bandgap semiconductor, and argon bombardment is almost like a sand blasting process, except we're using argon atoms. So you accelerate argon atoms at your surface and it cleans any contamination off the surface. And when we're talking about contamination, we mean things like the thin layer of water. There's moisture in the air around it, so on the top of any surface there's a thin layer of water. And when you're talking about nanostructures, a thin layer of water on the bulk scale becomes quite a thick layer in comparison to the rest of the structure. It can also be carbon. There's carbon in the air around us, and this will also adhere to the surface, and this can affect your conductivity measurement, which we saw. So what we did is we landed two probes on a series of nanowires and measured the resistance. We then divided it by the probe separation so we could average all our resistance measurements together and form a comparison. And what we found was the resistance was fairly high, as you can see from this graph, or relatively high compared to what we're about to talk about. And if you look at the error bars, which are these little lines coming off each data point, you can see that these are quite large, and this is an indication of the spread. So our values were very inconsistent for resistance. What we did then was use a very light argon bombardment on the nanowires, and as you can see, the resistance dropped massively. It dropped several orders of magnitude, and those error bars really tightened up. So the actual measurements were far more consistent. If we look at the PL graph, you can see that there's no real difference between before and after this light argon bombardment. And also if we look at the SEM images of the nanowires, you can't see any physical difference. However, as we started turning up the argon bombardment power, we started doing damage to the nanowires. You can see this in the series of SEM images. And by the end of it, when we were using pretty much the full power of the gun, you can see that the surface of the nanowire has been stripped off. You can see the shadow that's been left around it. So we've actually removed the surface. And if we look at the PL, the actual number of defects has actually gone down, as you can see in this graph, where we've just overlaid the PL results. The defect peak is decreasing. So what I initially hypothesized was that as you argon bombardment, you do damage to the surface, obviously done, and this would increase the number of defects, but it's actually gone down. And the reason for this is because we've actually stripped the surface. So in a crystal structure, the defects make their way out to the surface of the structure, or the near surface, and this is to minimize what's known as the lattice energy. So on a crystal, the actual defects are normally on the surface, and because we've stripped that surface away, we've actually removed the defects. And interestingly, what this does with the conductivity, or the resistance, is as you remove the defects, the resistance starts to go up. So again, this is sort of counterintuitive. You thought if you remove the defects, then your resistance would go down because you have a more pure structure. However, with zinc oxide, the oxygen vacancies are actually responsible for the conductivity. So you remember I said that when you remove the oxygen, you can leave some electrons hanging in free space. These electrons actually contribute to the conductivity of the nanostructure, or zinc oxide. So as we remove the surface, remove the defects, which is removing the zinc oxide, also the oxygen vacancies. Therefore, we are actually removing the conductivity, as you're removing these extra electrons from the zinc. So as you can see, the resistance starts going back up again, and it doesn't go up by a number of orders of magnitude. So this paper is open access, so if you want to have a read of it, there's a link down below, and anybody in the world can access it and view it and read it at your pleasure. Hope you found this video interesting. I've also down below included some links if you want to cite this paper. If you are researching, you're doing research into zinc oxide and you want to reference this paper, then please feel free to do so. Anyway, hope to see you again on another video very soon where I explain my research.